Up until now, we used this formula over here to calculate amount of heat being lost or received if the substance was warming up or cooling down. Now let's talk about heat received or lost during the change in the physical state of the matter. We know that there is no increase in temperature or decrease in temperature during that time. During boiling or condensation, melting or freezing, the temperature remains the same. So we cannot use this formula. During that period of time, there is no change in temperature. Also, we should reconsider specific heat capacity, because specific heat capacity tells us how much heat absorbed per gram per degree Celsius. But since there is no change in temperature, over here we have to replace specific heat capacity with heat of fusion or heat of vaporization if we want to calculate amount of heat that went into melting something or into boiling something, or how much heat was released when a substance was condensating or freezing. To calculate the amount of heat that was absorbed or lost by the substance during the change of physical state, we will have alternated formulas. We will calculate heat as the product of mass times heat of fusion when substance is melting or freezing, or heat will be calculated as mass times heat of vaporization when the substance is boiling or condensing. By now you should be familiar with the definition of specific heat capacity. It is the amount of energy required to change the temperature of 1 gram of substance by 1 degree Celsius or 1 degree Kelvin. However, the heat of fusion will not be connected to the change in the degrees of Celsius, because during the melting or freezing there would be no change in temperature. So heat of fusion is the amount of energy required to change a gram of substance from the solid to the liquid state. Heat of fusion for water is well-known number. It's 334 joules per gram. It means that if I have 1 gram of ice, I would need to transfer 334 joules of energy into it to melt it completely. Now, heat of vaporization also independent of temperature. It is the amount of energy required to change a gram of substance from the liquid to the gaseous state. Heat of vaporization for water is also well known. It is 2260 joules per gram. It means if I have 1 gram of liquid water, I would need to transfer into it 2260 joules of energy to make all of it to become a water vapor. Here are our basic formulas for the calculations of heat. When something is warming up or cooling down, we will be using this formula: the mass times the specific heat capacity times the change in temperature. When melting or freezing is involved, we will be using this formula: the product of mass and heat of fusion. When something is boiling or condensing, we will be using this formula: mass times heat of vaporization. Heat of fusion of water and heat of vaporization of water, as well as specific heat capacity of liquid water, are reported in your reference tables on the first page in Table B, so know where to find them. Here are some sample problems. What amount of heat is required to completely melt a 29.95 gram sample of solid water at 0 degrees Celsius? So we assume that our piece of ice is already at 0 degrees Celsius, totally prepared to melt. So how much energy would it take to melt it? We'll be using the formula of mass times heat of fusion. Mass is given to us in the problem, and heat of fusion we can look up in our reference table. So the amount of heat required here would be 10,000 joules of energy. How much energy is required to boil 150 grams of water? So since we're talking about boiling, we should be using heat of vaporization. So here's our formula. We're given mass, and we can look up heat of vaporization in the reference table. So the boiling of 150 grams of water will require 339,000 joules. And if we will represent our number in the correct number of significant figures, then it will be rounded up to 4,400,000 joules or 440 kilojoules. And since it's boiling we're talking about, this process is endothermic. Take a moment to read this problem. Now, let's consider what we know about water. Water is a liquid at room temperature. At 25 degrees Celsius, the water would be in the liquid state. The water boils at 100 degrees Celsius, and when temperature of the water sample is above 100 degrees Celsius, water is in the vapor form, in the gaseous form. So practically we have three stages in this problem. First, we have a stage of liquid water warming up from 25 degrees to the boiling point of 100 degrees. That would be amount of heat that goes into warming up liquid. Then we have to calculate the amount of heat that goes into the boiling of 200 grams of water. And then the last stage would be calculating how much heat goes into the water vapor as we're warming it up from 100 degrees to 125 degrees Celsius. We will use formula Q mc delta T for calculation of the heat that went into the warming up liquid from 25 degrees to 100. We will use mass times heat of vaporization to calculate amount of heat that went into boiling 200 grams of water, and then we will calculate how much energy went into warming up gas from 100 degrees Celsius to 125 using the old-fashioned Q equals mc delta T formula. But we need to pay attention that the heat of specific heat capacity for liquid water is different from the specific heat capacity for the gaseous water. Here are our calculations. So here's the first one, warming up of water from 25 to 100 degrees. Mass times specific heat capacity of liquid water times the change in temperature, 75 degrees Celsius. Then calculation of how much energy went into boiling 200 grams of water. So here is 200 grams multiplied by heat of vaporization. And then calculation of how much energy it takes to warm up gaseous water vapor from 100 degrees to 125. So 200 grams times specific heat capacity of water vapor, and then times difference in temperature that is achieved from 100 to 125, it is 25 degrees Celsius. To find out how much energy went into the entire process of raising temperature of that water sample from 25 degrees to 125, I need to add all these three numbers up.